Hello and welcome to Business Calculus Locating Vertical Asymptotes. The vertical line x equals a is a vertical asymptote of the graph y equals f of x if f of x approaches infinity or if f of x approaches negative infinity as x approaches a from the left or x approaches a from the right. That is, if f either increases or decreases without bound as x approaches a from the left or the right. In order to find vertical asymptotes, we want to look at the properties of polynomials and rational functions. If f is a polynomial function, we know that for any real number a, the limit as x approaches a of f of x is equal to f of a. This value is always finite, so we know that polynomial functions have no vertical asymptotes. Now, for rational functions, r of x, we think of them as being a numerator function, n of x, divided by a denominator function, d of x. If we have that the denominator function at a point c is equal to 0, and the numerator function at point c is not equal to 0, then the line x equals c is going to be a vertical asymptote of the graph of f. Let's look at an example. The function f of x equals x squared plus x minus 2 divided by x squared minus 1. We would like to know when the function of this denominator is equal to 0 because those values of x are the only possibilities for vertical asymptotes. By factoring x squared minus 1 into x minus 1 and x plus 1, we know that this is only 0 if f is equal to 1 or f is equal to negative 1. Now we check those values against the numerator. By factoring the numerator, we can determine that it is equal to 0 only when x is equal to 1 of the two values that we had previously, 1 and negative 1. So x equals negative 1 is the only possible vertical asymptote of f of x. But what about when x approaches 1? We'd also like to know the behavior of the function near this value, and in order to determine that, we treat it like a 0 divided by 0 indeterminate form. We look at the limit as x approaches 1 of our function. We factor it into x minus 1 times x plus 2 divided by x minus 1 times x plus 1. We divide out the like terms, and we're left with the limit as x approaches 1 of x plus 2 divided by x plus 1, which, because the denominator of that function is not equal to 0 when x is equal to 1, we can just plug in 1 and get 3/2. Continuing on with example 1, we see that we have the limit from the left, on the left-hand side of our screen here, and we are plugging in values that are getting progressively closer to 1 from the left. And as we do that, our function gets larger and larger in the negative sense, and trends down in this direction. As such, we say that the limit from the left as x approaches negative 1 of f of x is equal to negative infinity. On the right-hand side, we check the limits coming from the other direction. We plug in numbers that get progressively closer to negative 1 from the right, and see that our function is increasing this time without bound. And as such, we say that the limit as x approaches negative 1 from the right is equal to positive infinity, as we're trending in this direction. Okay? Lastly, for this example, we see here our hole in the graph. There's an unfilled in circle, and this represents the ordered pair 1, 3/2, and this is a hole in the graph because 1 is not in the domain, because if I plug it into the denominator, I get 0. But we can evaluate its limit, as we had on the previous slide, to determine how the function behaves near that value and determine the limit as x approaches 1, even if the function itself does not exist at that point. For another example, let's try g of x equals x squared plus 20 divided by 5 times the quantity x minus 2 squared. When is the denominator of this function equal to 0? By looking at x minus 2 squared, we see that this is 0 only when x equals 2. For these values, we check to see when the numerator is not equal to 0, and we see that the numerator is always positive because x squared is a non-negative quantity, and I'm adding to it a positive number, 20. So x equals 2 is the only possible vertical asymptote, and since it's the only value when the denominator equals 0, I don't have to investigate any additional values for x. Here we have graphed similarly to the previous slide our function, and we see that as we approach 2 from the left, our function grows very, very quickly, so fast that it flies off screen. And we get similar behavior when we approach x equals 2 from the right. Again, the function just takes off. It gets very, very large very, very quickly in my approach to 2. Now, because in this situation we see that the limit from the left and the limit from the right agree that the limit as x approaches 2 of f of x is actually equal to infinity, because these limits exist even though they're technically unbounded, but since they go to the same infinity, we say that the limit of the function overall is positive infinity. Now, what I would like you to do is to locate all of the vertical asymptotes of the function f of x equals x minus 1 divided by x plus 4 quantity squared. Here's some possible responses. And thank you very much for listening.